Welcome to the second week of our course. We are in the first module, Introduction to Systems, and in this week we enter the second section of this module, which is about complexity science. We are going to have 3 weeks on this topic. The first week, which is this week, week 2, we are going to discuss the principles. We are going to get to know complex systems and talk about their attributes and do some simulations on various attributes of complex attributes and basically properties of complex systems. For the remainder of this section, the week 3 and 4, we will be focusing on two of the most important topics in complex systems. One, and both of them related to the measure of complexity or measurement issues in complex systems. We will be talking about information theory as well as fractals. But for this week, let's focus on complex systems, their definition or its definition, and what type of systems can be considered complex, and what are the difficulties of studying these systems. Our approach to understand complex systems is not going to start with the definition, and I'm going to clarify why. But for now, I'm going to focus on two important issues. One is that what type of problems or issues or topics or subject areas can be studied or will be studied or should be studied with complex systems and complexity science. And two, from a disciplinary perspective, what type of basically interdiscipline or transdiscipline is complexity science. I will talk about the differences, what is multidisciplinary, what's interdisciplinary when we get there, but these are two topics that I'm willing to address. The first and the most important one, focusing on the top type of problems and the areas that can be addressed with complexity science. So if we have level of regularity and randomness on one axis and the level of complexity on the other one, which is a product of these two, basically, regular and randomness, we are going to have something like this. And there are different type of problems can be studied. On the regular side of the story, as you can see on the lower left corner, these are very regular problems, deterministic systems that have very low complexity. Also, these are known as linear simple systems. This can be studying our solar system or most of the Newtonian basically world problems, and you're familiar with your high school physics about these problems, and we can write down simple, elegant, comprehensive formulas that can explain equations that can explain the entire problem, and we can formulate it, we can precisely predict the future of the system, and we can explain how the system works very well. So that's on one side of the story. If we add slightly if we go to the other opposite side of the issue, we have the first category, by the way, is the classical mechanics. That's the, as I said, it's very common in the high school physics that you have studied. On the other side, you have statistical mechanics, or we can address these using statistical science. Most of the statistics you have learned and we use, the tests that we have in statistics, and almost 90% of scientific studies we conduct follow those rules based on superposition and also homogeneity. which is introduced in the text that I have provided to you, can be addressed for using these basically techniques. The type of problems, however, is different. As you can see, almost no regulation exists here. We are dealing with the complete randomness. I'm refusing to use word chaos because it's a different type of story. Complete randomness. And these are the type of problems that statistical mechanics can handle, like gas problems. We are dealing with millions and billions and trillions of gas molecules that are moving in arbitrary ways. But it's easy to handle these problems despite having trillions of variables using simple averages. We can take the average of the all movements for the state and we can handle the problem relatively easily. So while it's completely random, it's not as regular as previous type of problem, still we can address that using well-established scientific methods in statistical mechanics. Now, slightly more randomness, but still in the realm of regulations, we are dealing with problems of quantum mechanics. This can be where is the electron in the atom at any given time. We don't know precisely where it is, but using the principles of quantum mechanics, we can have some understanding of these systems. Obviously, these systems are not as easy to predict as the regular systems because of some randomness. So we have errors. So we don't have a level of precisions we used to have in regular systems, but still we have a good understanding of these systems using quantum mechanics. Now, in the middle of this story, we have the main problem we are dealing with, and these are the complex systems. This is the area that we have as much as regulations as we have randomness. So this is the area that equally regularity and randomness contributing to these problems, and that makes it very difficult to study these systems. Complex systems basically are most of the systems you see in the culture and nature. So we are going to see some examples of these systems: your brain, your body, your immune system, most of the ecological systems, the entire earth, some of the systems we built, like, for example, spaceships, even very basic infrastructure systems like road networks or airlines or aviation industry, basically, and many other systems in nature like honeybees or a group of elephants, and you can find many other examples. I use the example of tree and jungle or forest. All of these are examples of complex systems, and we are going to see why. But the thing to remember studying complex systems is that these systems have more or less equal levels of regularity and randomness, and that's what make these systems very difficult to study.